Hi there. For this video, we'll be discussing the domain of rational expressions. Now I know that this playlist is all about rational equations, but this concept of domain of rational expressions is essential in determining and solving rational equations. So first, when we say domain, this refers to all the possible inputs or all the possible x that we can have in a given equation or expression. So if we have x plus 1, x out here can be any value. So we say that its domain is all real numbers. But if we have a rational expression, say 1 over x, note that the domain here is not all real numbers. Since in rational expressions, the denominator cannot be equal to 0. So we say that its domain is all real numbers except 0. Or we can also write it as x, there shouldn't be this one, it should be like this, it's the domain. Or we can write it as x is in R such that x is not equal to 0. So let's go on to our first example. If we have 2 over d minus 1, so our goal is to find the domain of this rational expression. Again, the key is, in rational expressions, the denominator cannot be equal to 0. So, we have d minus 1 is not equal to 0, and we can solve this like an equation. So we can move this to the right side, and we'll obtain d cannot be equal to 1. Indeed, if we plug in 1, this will become 2 over 0. So the domain is given by all real numbers except 1, or we can write it as d, the set containing d in R such that d is not equal to 1. And that is the domain. Let's have this next one. Let's have x plus 2 all over x squared plus 3x. We know that this cannot be equal to 0. But before we solve that one, we first factor it, since we can write this as x plus 2 over x times x plus 3. And so, when will this denominator be 0? Either if x is equal to 0, or if x plus 3 is equal to 0. Solving for this, we'll have x is equal to negative 3. So we know that x cannot be equal to 0 and x cannot be equal to negative 3. So our domain is given by all real numbers except 0 and negative 3. Or we can write it as x in R such that x is not equal to 0 and negative 3. Let's have this third example. Let's have 5 over 2x squared plus 8x plus 8. So again, we determine when will this denominator be equal to 0. So first, note that we can actually factor out a common factor of 2 in the denominator, since 8 can be written as 4 times 2. So we'll have here 5 over 2 times x squared plus 4x plus 4. And observe that this trinomial out here is a perfect square trinomial. So this factors into 2 times x plus 2 squared. And so we determine when will this denominator be 0. It will be 0 if this cannot be 0. So we focus on this. So x plus 2 will be 0 if, move this to the right side, if x is equal to negative 2. So we know that x cannot be equal to negative 2. So our domain is given by all real numbers except negative 2, or x in R such that x is not equal to negative 2. And that is the domain of this rational expression. Let's have this next example. Let's have 3z minus 15 over z squared minus 25. Now first, again, our goal is to make this denominator in linear factors, so we can easily determine what values will make it 0. So we'll have here, this is a difference of 2 squares. Indeed, this is a square and 25 is equal to 5 squared. So this factors into the sum z plus 5 and the difference z minus 5. How about the numerator? Well, we don't really need to factor it, but for the explanation purposes, we'll factor it out. So since there is a common factor of 3 out here, we can factor this as 3 times z minus 5. And what can you observe? Observe that there is a factor of z minus 5 in the numerator and in the denominator. Question is, do we cancel them out? The answer is no, since if we cancel this one out, the only factor that would make the denominator 0 will be negative 5. Z equals negative 5. But that is not true, since z equals 5 also makes the denominator 0. Indeed, if we plug in 5 out here, the denominator becomes 0. So although we know that in simplifying rational expression, we usually cancel out common terms in determining its domain, we don't do that. Instead, we disregard the numerator, so we can still treat the numerator as 3z minus 15 and just focus on the denominator. So when will this denominator be 0? If z plus 5 is equal to 0 or z minus 5 is equal to 0. The first will give us z equals negative 5. The second will give us z equals 5. So we know that z cannot be equal to -5 and z cannot be equal to 5. So our domain is given by all real numbers except positive -5, or we can write it as the set containing x that are all real numbers such that, our variable is z, such that z is not equal to positive -5. That is the answer. Let's move on to this second to the last example. Let's have 5 over x squared plus 7x plus 12. Now in here, it's not quite easy to see what values of x will make the denominator 0, but observe that this is a quadratic trinomial. So we can factor it out. So to do this, we first observe the last term and check out its factors. So we have 12. It can be 12 times 1. We can have 6 times 2 or 4 times 3. And we determine that which among these factors, when we add, will result to the middle term. Clearly, it is 4 plus 3. So we factor this one as x plus 4 times x plus 3. So we now write this one as 5 over x plus 4 times x plus 3. And to determine when will this denominator be equal to 0, we have x plus 4 equals 0 and x plus 3 equals 0. X plus 4 is equal to 0 when x is equal to -4. X plus 3 is equal to 0 when x is equal to -3. And so our domain is given by all real numbers except it cannot be -3 and -4. Or we can write it as the set of x in R such that x is not equal to -3 and -4. That is the answer for this. Finally, let's have 1 over x squared plus 1. Now this one is quite tricky, but intuitively, let's think about when will this denominator be equal to 0? Well, take note that when we square a number, the outcome is always positive. So, a positive number plus a positive number will always be positive. And if it is positive, it is not equal to 0. So what does that mean? That means that all real numbers satisfies this expression. So our domain is simply all real numbers. Or we can write it as x in R such that, there's no such that since all values of x satisfies this expression. And why is that? Well, if we view it in complex numbers, since this one actually has a complex root, since we can write this one as x squared minus negative 1. Applying the difference of two squares, this is equal to x plus the square root of negative 1 times x minus the square root of negative 1, or x plus I times x minus I. So the values that would make it 0 are x equals positive negative I. But I is not a real number. Since we're only dealing with real numbers, then the domain is the whole real number system. And that is the answer for this. And that's how to get the domain of rational expressions in general. To end this one, here are two exercises that you can work on. First, we have y squared plus 2y minus 5 over, this should be 3 times 3y cubed minus 3y squared, and the next one is 5 over 3a squared minus 2a minus 5. So as you can see, even though we're dealing with equations and we discuss here rational expressions, as you can see, the concept of equations is very important in understanding how to get its domain. If you're questioning what the purpose of getting the domain is, we'll be using this concept in solving for rational equations. Since by getting the domain, we restrict the values of x that we have in our answer for solving the rational equation. So for instance, if after solving the rational equation, we obtain positive negative 1, but in the denominator, we have a factor of x minus 1, say. That means that our final answer cannot have a value of positive 1. So our final answer will only be x equals negative 1. So that is the purpose of the domain, to make sure we don't have solutions that are invalid. So that's it. I hope you enjoyed this one, and feel free to comment down below your answers and solutions to these two exercises. So that's it, and that's all for this video.